So we've been talking about substitution reactions and how they're useful in synthesis to make new carbon-carbon bonds, new carbon-nitrogen bonds, new carbon-halogen bonds, and so on. So now we're going to move on to talking about elimination reactions that are useful in synthesis. And so remember, typically substitution and elimination reactions occur on sp3 hybridized carbons, but we can do E2 reactions with halogens that are attached to sp2 hybridized carbons to convert alkenes to alkynes. And so we call this a vinyl halide. So vinyl halide. And this means that the halogen is attached directly to one of the carbons on the alkene. And so we can take vinyl halides and convert them to alkynes. So let's take a look at the mechanism. Like I said, this goes through an E2 reaction. And so we know that in an E2 reaction, we're going to pull off a hydrogen from the beta carbon. So we identify the leaving group is connected here. We go to the beta carbon, which is going to be here, and we pull this hydrogen off. Remember that sp2 hybridized carbons, the hydrogens that are attached, pKa is about 42. sp3 hybridized carbons, the pKa is about 50, and so this one is more acidic, and so therefore that's why we pull this one off instead of these two shown here. Our base here is sodium hydride. Sodium doesn't mean anything. Remember that sodium hydride is a source of H- that acts as a base, and so this comes in and grabs our proton, and we go through our E2 mechanism to get to our alkyne. Also remember that we call this an internal alkyne, and that's because our two carbons of the alkyne are in the inner parts of our chain. In addition, when you're doing exams and stuff, make sure you count your carbons always. So we have 1, 2, 3, 4, 5, 6 carbons in our starting material. Again, we have 1, 2, 3, 4, 5, 6 carbons in our product. Lastly, since this proton is not very easy to pull off, you need to use a very strong base for this reaction to occur. And so something like sodium hydride, LDA, or sodium amide, which I'll talk a little bit more about in just a second. One thing to keep in mind is if we are making an internal alkyne, we just treat it with the base and we're done, we get to our final product. If we make an terminal alkyne where one of the carbons is attached to the hydrogen, remember this hydrogen has a pKa of about 25, and so it's even more acidic than the proton we would pull off of this molecule. And so as soon as this forms, this gets deprotonated to make the anion, and so we need to use an acid workup. And then we also need to use two equivalents of LDA, one to deprotonate this, and then one to deprotonate this, so that we can get all of our starting material converted to our product. So let's take a look at the mechanism for this reaction. We identify the leaving groups attached to the alpha carbon, so we go over to the beta carbon and pull off the proton. Note, in the case of going from alkenes to alkynes, you can pull off hydrogens that are both cis or trans to the leaving group. But remember, when we're using alkanes, the hydrogen must be anti to the leaving group. And so in this case, we can have the hydrogen here, or it would still react if it was here. So we take LDA, lithium doesn't mean anything, we draw out the diisopropyl amide shown here, and so this comes in, grabs that beta hydrogen, we move our electrons down, and we kick out our leaving group. Once this happens, we get to a compound that looks like this. Remember to count your carbons. We got 1, 2, 3, we got 1, 2, 3 here. As soon as this forms, this proton that's hanging out right here is now more acidic than this one, so any LDA that is floating around is going to come in and deprotonate this, giving us a anion on our alkyne, and so that is why we need to use two equivalents of LDA in order to get to here. Then this floats around forever because there's no protons for it to pick up. So now we go to step 2, HCl and H2O. Remember, this equals H3O+, so I draw that out here. And this protonates our terminal alkyne to get us to our final neutral product. So this workup step is required when we make terminal alkynes. So let's talk about another elimination reaction that we can use to make alkynes. So we just talked about converting vinyl halides, so halides their own alkenes into alkynes. Now we can take dihaloalkanes. So we have an alkane molecule, no double bonds on it. With two halides, we can convert to an alkyne. How do we do this? We use excess sodium amide. You might also see this written as 3 equivalents for this type of reaction. They both mean the same thing. And then we make a terminal alkyne in both cases. So we have a second step. I wrote H3O plus this time instead of HCl, H2O. But it's the same thing. We just protonate our final molecule to get the neutral organic product. So we see that we have two different types of dihaloalkanes. We have vicinal dihalides. This is where our halogens are on carbons that are next to each other. And then we call this a geminal dihalide, where we have the halogens are both attached to the same carbon. So let's walk through the mechanism for one of these. If you look at the vicinal dihalide up here at the top, we know that sodium amide is a strong base, which I'll talk about in just a second. And then we know when we do elimination reactions, we need to identify the leaving group. So we have one leaving group attached here and one attached here. So let's just focus on one of those for now. This one, if it's attached here, we go to the carbon next to it and we pull that proton off in an E2 mechanism. So sodium doesn't mean anything. I draw out my negatively charged nitrogen. Again, this is a strong base. So it grabs our proton, we move our electrons down, and we kick off our halogen. After this happens, we get to a vinyl halide just like we had before. So if you follow this through, the chlorine's gone now and we have a double bond here, and this chlorine is still here. So now we have a vinyl halide, and so the mechanism proceeds just like I showed earlier. We can pull off either one of these protons. The trans one is going to be a little bit faster than the cis one, and so I'll just pull off the trans one. We use our second equivalent of sodium amide, grab that proton, move those electrons down, kick off our leaving group, and so we've done two E2 mechanisms here, and this gets us to our terminal alkyne. And remember, as soon as this alkyne's formed, this proton is more acidic than these are, and so we need a third equivalent of sodium amide or whatever strong base we're using, and so that would come in and deprotonate our alkyne, giving us a carb anion that looks like this, and then this would float around forever until we dump in our acid workup step. So we have H3O plus, which then protonates our terminal alkyne, getting us to our neutral organic molecule. So the geminal halide mechanism is very similar. You would just pull both protons off of this carbon. You should go through that mechanism yourself. So we talked about going from vinyl halides, so alkenes to alkynes. We talked about going from dihaloalkanes to alkynes. So those are both elimination reactions. And so we're going to look at one last elimination reaction. It's called the Hofmann elimination. And so we can take amines, primary amines in particular, and eliminate them to give alkene products. Although nitrogen is not a good leaving group no matter what we do to it, if we use some heat and we throw in silver oxide, we can get this reaction to take place. Keep in mind, silver oxide is very important for this reaction. It would not occur without it. Notice we make the less substituted alkene, so we could pull a proton off of here, which would make the disubstituted alkene, or we could pull a proton off of here, giving us the monosubstituted alkene. We get this as our major product, and so we call this the anti-Zaitsev product. I've talked about this a lot during the semester. I've just never given it a name. And so the idea that we want to make the more stable alkene is called Zaitsev's rule, which I'll talk about in just a second. And when we make the less substituted alkene, we call it the anti-Zaitsev product. So like I said, this is nothing new. We've talked about this during the semester. Zaitsev's rule means that the major elimination product gives the more stable alkene, which is the most substituted one. But again, in the Hofmann elimination, we get the anti-Zaitsev product, so the least stable one. So why do we get the anti-Zaitsev product or the least substituted alkene? Let's walk through the mechanism. So first thing that we notice, nitrogen we know is a nucleophile, and we have methyl iodide, so an alkyl halide, and this is going to proceed through an SN2 reaction. So our lone pair on our nitrogen is able to attack the carbon of the methyl iodide, and so we get alkylation of the nitrogen. This gives us an intermediate that looks like this shown here. So our nitrogen went from having 3 bonds to 4. It gets a positive charge shown here. And then once this happens, we get a proton transfer. So remember that nitrogens are weakly basic, and so it is going to deprotonate this, another molecule anyway. And so we would have another starting material, amine. It would come in and deprotonate this nitrogen. So just draw out my hydrogens. Grab that hydrogen on there, give the electrons back to the nitrogen, giving us a neutral molecule. And so we've substituted one of these hydrogens for a methyl group. Remember that primary amines are very nucleophilic, and then once we get here, this is even more nucleophilic because of the donating ability of the carbons. And so this happens a couple more times. So we get a couple more SN2 reactions, a couple more proton transfers, and we get to an ammonium salt. So we look something like this. Again, this is not a very good leaving group. But if we throw in silver oxide with some water and heat, we can get the elimination to work. And so why does this happen? Well, after all of these alkylations, we get this ammonium salt here, where iodide from our SN2 reaction as our counterion. We throw in silver oxide, and that essentially what it does in water is it exchanges this salt from the iodide anion to having a hydroxide anion. And so it essentially switches our salt from this to this. Remember, I minus, terrible base. Hydroxide, very good base. And so since we're heating it, we have a very good base. We are able to do our elimination reaction. Again, in the Hofmann elimination, we get the anti-Zaitsev product, so the less substituted alkene. So we pull the proton off of here, we move these electrons down, and we kick off our nitrogen leaving group to get to our product. And so this is an E2 mechanism shown here. You may be asking yourself, why do we form the less stable alkene in this case when everything wants to be more stable? Well, let's take a look at the Newman projection of our ammonium salt intermediate. So if I draw that back out, we have this here, and then we're going to draw a Newman projection looking down the C1, C2 bond, and then we'll draw a Newman projection looking down the C2, C3 bond. And remember, for eliminations on sp3 carbons, our hydrogen has to be anti to the leaving group. So if we draw our Newman projection looking down this bond, remember this circle represents the back carbon. The dot in the middle represents this front carbon. This front carbon has 3 hydrogens on it, and so it doesn't really matter how we draw this out. Like this. And then back here on our back carbon, we have an ethyl group coming off of it. Since there's no stereochemistry drawn, it doesn't really matter where we draw this on the circle, so I'm just going to draw it down here. So there's our ethyl group. Draw out my ammonium up here, and then we have a hydrogen coming off of there. So you can see that in this Newman projection, we have a hydrogen that is anti to our leaving group. So remember, this is 180 degrees. And so we can easily pull off this proton to eliminate this leaving group. Now I'm going to redraw it over here so it's easier to see. If we do a Newman projection looking down this C2-C3 bond, so where C3 is the first carbon we're looking at, again, our circle represents this back carbon, and this dot represents our front carbon. Off of this front carbon, we have a methyl group and 2 hydrogens. Again, it doesn't really matter how we draw it. Just to stay consistent with this, I'm going to draw this front carbon out like this. And then we also have 2 hydrogens coming off of there. Again, it doesn't really matter where I put those. Then on my back carbon, I have this ammonium salt coming off. And I have a methyl group coming off. And I have a hydrogen coming off. Again, it doesn't really matter how I draw this. And so we see in this case, we easily have a hydrogen that is anti. But notice in this case, when our hydrogen is anti to the leaving group, we have our methyl group hanging out over here. Remember, it has a bunch of hydrogens off of it. And so we have a steric clash between these two. And so this is a highly unfavorable Newman projection. If we rotate this around so that we relieve this strain, that means our CH3 is going to be at the bottom and our 2 hydrogens are going to be up here. I cleared this off a little bit, but if we rotate this so that this clash is not happening, we're going to bring our methyl group down to here, and then our 2 hydrogens will be up here. So if we draw that out, this would now be our CH3, and this would be our hydrogen. So all I've done is rotate that bond. That relieves the steric clash between the methyl group and the nitrogen. But now we have no hydrogen that is anti to our leaving group. And so this is why we get the anti-Zaitsev product, or the less substituted alkene, when we do an Hofmann elimination reaction.